In today's video, we're going to talk about exponential functions. You already know what an exponent is, and an exponent is like 2 squared, and the number up in the top is the exponent. 2 squared would be 2 times 2, and how we can turn this into a function. So this is the exponent. How we turn this into a function is we have a function that depends on x, and it's going to be equal to, we need something to an exponent. Let's pretend we're using this right now. So if f of x was equal to 2 squared, 2 to the second power, there's nowhere to put this x. Since there's nowhere to put this x over here, and this is called an exponential function, we're going to erase the exponent, and the exponent is going to go, or the x is going to be the exponent. The variable is the exponent. So in an exponential function, we have the variable as an exponent. The general form is f of x equals a times b to the power of x. In this, a is, it's like a coefficient. It basically is a coefficient. So a is a number that isn't 0. B is, it's between 0 and 1. Or greater than 1. So it's a positive number. B is a positive number that's bigger than 0, but not equal to 1, basically. A is anything that's not 0. It can be positive or negative. And x is the exponent. So what this means is we're going to have a changing exponent. So let's graph an easy example of this. F of x equals 2 to the x, like we had a second ago. If I make a table of this, zero, 1, 2, 3. 2 to the 0 is the first one. To the 0 power is 1. 2 to the first power is next, is 2. 2 to the second power is 4. 2 to the third power, 8. And let's go one more. 2 to the fourth power, 16. 0 goes with 1. 1 goes with 2. And we had a half. A half goes with 1.4. 2 goes with 4. 3 goes with 8. And then 4 is way off the chart. It's going to be double of 8. So if we connect these dots, look at that picture. Does that look familiar to you? It should, because we just spent a whole lot of time graphing quadratics. But let's compare this to a quadratic. So if this was f of x, then if we had a quadratic that was g of x equals x squared, then this table, not y, x and g of x. Oh, I made that mistake on the left. Oh well. For this table of x and g of x, if we do 0, 1, 2, 3, then we would have 0, 1, 4, 9. So you can see that the tables, this one has 0, 0. This one has 0, 1. This one has 1, 2. This one has 1, 1. 2, 4. 2, 4. 3, 8. 3, 9. So even though they have some numbers in common, and they are close, these two functions do not look the same. I'll go ahead and graph the quadratic next to it in purple. So these are very similar pictures, but not the same. And if we compare the left sides, the parabola would look like this. And let's compare the left side of the exponential, blue. So I'm going to make a new table, but it's going to be the same function for the exponential, x and 2 to the x power. We're going to do -1, -2, -3, -4. 2 to the -1 is 1 over 2. 2 to the -2 power is 1 over 4. 2 to the -3rd power is 1 over 8. And 2 to the -4th power would be 1 over 16. You can see that we have similar numbers, 1, 2, 4, 8, 16. So we have 1, 2, 4, 8, 16. These are fractions. So let's graph these fractions. Let's go back 1, 2, 3, 4. And I'm going to zoom in a lot. The first one was -1, 1/2. And then it was -2, 1/4. Then -3, 1/8. Then -4, 1/16. So if I add these dots, it's going to look like that. So the exponential function and the parabola, they look completely different once you get into the negative numbers. Once you pass, so a parabola has an axis of symmetry, what the exponential function has, this is called an asymptote. And what an asymptote means is we approach a number but never get there. And let's see what that number is. Let's plug in -100. 2 to the -100 equals 1 over 2 to the 100th power, which is 1 over 1.26 times 10 to the 30th power. So let's compare. This would be 1 over 1.6 times 10 to the first power. So if we compare 2 to the -100 to 2 to the -4th, 2 to the -4th power would be 1 over 1.6 times 10 to the 1, while this one is 1 over 1.26 times 10 to the 30th power. So that means that this number has so many more zeros, so many more digits. If I didn't put this thing, if I just put all those zeros, it would be so much bigger. If you're dividing by a big number, so let's do 1 divided by a huge number, you can see what's happening because this arrow is going to the left. It's going to be, well, it's not going to be, it's going to get close to 0. The bigger the number is in the denominator, the closer your answer will be to 0. And whenever we have a function that has infinite numbers, because we can plug anything in here for x, the more negative the exponent is, the closer that answer is going to be to 0. F of x equals 2 times 5 to the x. We're going to make a table. -1, I'll do -2. -2, -1, 0, 1, 2, 3. So we have 2 times 5 to the negative 2. So that's 2 over 5 squared, which is 25. 2 over 25. Negative 1. 2 times 5 to the negative 1 equals 2 over 5. 2 to the 0. Oh, not 2 to the 0. 2 times 5 to the 0. So that's 2 times 1 equals 2. 2 times 5 to the 1. That's 2 times 5, which is 10. 2 times 5 squared. That's 2 times 25, so it's 50. 2 times 3, nope, 5 to the third. 5 to the third is 125 times 2 is 250. Let's graph these. Negative 1 was 2 over 5. 0 was 2. 1 was 10, so that's about halfway to 25. 2 was 50. 3, 250. Connect these dots. Oh, that was terrible. That's what it'll look like when you're going to the right. And in fact, in our graphing calculators that we have at the school, they will only show like this much of the graph because they can't do this piece here where it's almost flat. The graphing calculator can't do this almost flat but not flat line. This is not a flat line. This asymptote is not flat. The asymptote is not flat, but it's like as close to flat as you can get. It's at a very slight tilt because none of these answers are repeating. It's just that they are so incredibly close together. Each spot on the asymptote, the y is only changing by such a little tiny amount that it's as close to flat as you can be without being flat. We would call it a horizontal asymptote. This would be called a horizontal asymptote, and there would not be a vertical asymptote here. Let's notice some things. When I plugged in 0, I got the number 2. Up here, when I plugged in 0, I got the number 1. So the y-intercept is not connected to this base number. The y-intercept is not connected to what is being raised to the exponent. The y-intercept of an exponential graph is connected to this number. Right here it's a 2. Well, what's in front of this 2 here? You would say it's nothing. Well, it's actually the invisible number 1 because 1 times 2 is just 2. So whether you put the 1 there or not, you can make it there because math says 1 times something is itself. So the y-intercept of an exponential graph comes from the a in the formula. What b tells you, what b is going to tell you is the growth rate. The growth rate or decay rate the growth or the decay rate of an exponential function comes from b in the formula. So what is being raised to the exponent is going to tell you how fast it's growing or how fast it's decaying. And what do I mean by that? Well, let's compare this. Let's compare 250 to 50. How many times bigger is 250 than 50? Well, 250 divided by 50, this is going to fit in there 5 times. Let's compare these. 50 and 10. How many times bigger is 50 than 10? 5 times. 2 to 2/5. 2/5 times 5 gets you to 2 because it would cancel out the denominator. 2/5 to 2/25. Again, it's another factor of 5. So that would mean that as we're going down this table, each integer increment for x results in a 5 times growth in y. Every integer that we go up for x resulted in 5 times growth in the y. For here, we went from 1 to 2. That's 2x, 2x, 2x. In this one, the growth is a factor of 2 times. And in this one, the y increased by 5 times.